Hi dear students, welcome to my channel. Hope all of you are doing good. So in this video, I will start the S block chapter from class 11. I will make 2-3 videos on this chapter because in a single video it will not be possible to cover whole chapter. So I will make 2-3 videos one by one. I will finish it by the end of this week. So if you like this first video, then subscribe and don't forget to share, and don't forget to click on the bell icon button so that whenever I upload the new videos, it goes in your notification. Okay, so let's start without delaying. I'm starting. So as block, it consists of two group, 1A and group 2A. So 1A element contains lithium, sodium, potassium, cesium, rubidium, sorry, potassium, then rubidium, then cesium, then francium. And the group 2 elements are beryllium, magnesium, calcium, strontium, barium, radium. Okay, so if I talk about their atomic number, so it is 3. So 8 plus it will be 11, and it will be 19, 37, cesium is 55, francium is 87. So how can you remember this? So if you move from here to here, it will be 8 plus, and from sodium to potassium, 8 plus, potassium to rubidium, 18 plus, and rubidium to cesium, also 18 plus, and cesium to francium, 32 plus. Okay, again similarly here it will start from 4, so 12, then 20, then it will be 38, then it will be 56, then 88. Okay, so these are about the atomic number. Now this group 1 elements, these group 1 elements are also called alkali metal, and these group 2 elements are called alkaline earth metal. Why it is so called, I will come later on. Alkaline earth metal. Okay, now I will go with group 1 elements firstly, then after finishing this group 1 element, I will go with group 2 element. Okay, now you can see lithium is diagonally related with the magnesium, okay, so this lithium and magnesium will have some similar properties, will exhibit some similar properties because of their diagonal relationship. Okay, so they will have some similar properties because of the diagonal relationship. As we know, diagonal. This is the elements which are diagonal in the periodic table. In this diagonal relationship, what we know? We know the elements which are diagonal to each other, their properties is same because of having almost similar size, for which some of the properties becomes similar. Okay, now I will move with group 1 elements. Okay, so group 1 elements, they are called alkali metals. Alkali metals. So why they are so called? Why they are so called? So this is because the alkali metal this is because after after not after, so when this metal react with, so when this metal react with water, they convert into hydroxide. They convert into hydroxide, for which the solution becomes alkaline or basic in nature. That's why they are known as alkali metal. Alkali metal. For example, if I react with sodium water, it will convert into NaOH. Okay, so when these metals, group 1 element, all metals react with water, so they will form a alkaline, a alkali, or a base. Okay, and because of which the whole solution becomes alkaline in nature. That's why they are called alkali metal. Okay, now next coming to next, this alkali metal does not exist in free state in nature. In nature, that does not exist in free state. Why? So this is because alkali metal has valency 1. Okay, so they can easily lose this electron to get inert gas like electronic configuration. If I give example, then it will be more clear to you. So they will lose electron to get the electronic. That means to fulfill their octet. To fulfill their octet. Octet means 8 electron in the outermost shell. So alkali metal has valency 1, so they can easily lose the electron to get inert gas like electronic configuration and convert into cation. For which they easily react. They easily react with atmospheric oxygen. Atmospheric oxygen and exist as oxide in nature. Okay, for examples, like if I talk about sodium, lithium. So lithium has 3 electrons, so electronic configuration 2,1. Sodium has 11 electron, its electronic configuration 2,8,1. So if it loses 1 electron, lithium plus, it will convert into lithium plus 1. Its electronic configuration will be 2. That means helium like electronic configuration. Sodium, if it loses 1 electron, it will convert into 2,8. So it fulfill its octet. Again, potassium, it has a atomic number 19, so electronic configuration 2,8,8,1. If it loses 1 electron, it will convert into K plus, then its electronic configuration will be 2,8,8. Okay, so they are getting 8 electron in the outermost shell. It means they are getting electronic configuration as like inert gas. Okay, so they can easily lose 1 electron, and because of this they react with oxygen that is available in nature, so they react with oxygen and convert into oxide. So when this Na2 sodium react with water, when sodium reacts with oxygen, so it will convert into Na2O. Okay, so like that they will exist in that does so like that they will exist in oxide state, not in a free state. Okay, now among these group 1 element, this francium is a radioactive element. So this one is radioactive element. Radioactive element means it will emit alpha, beta, gamma ray continuously. Okay, radioactive element. Now coming to next question. This is most important question. First, ionization enthalpy of alkali metal. first ionization enthalpy of alkali metal is less than alkaline earth metal, but the second ionization enthalpy of alkali metal is greater than alkaline earth metal. Why? Explain it. Okay, so I'm explaining this answer by taking an example. Let's say I have taken an element sodium from alkali metal and magnesium from alkaline earth metal. Okay, so atomic number of sodium is 11, its electronic configuration 1s2, 2s2, 2p6, 3s1, and magnesium has atomic number 12, its electronic configuration 1s2, 2s2, 2p6, 3s2. Okay, now if it loses one electron, it will convert into Na plus. So electron will be 10. 1s2, 2s2, 2p6. So it will lose electron from the outermost orbital. That means from 3s orbital. Okay. Now, in case of magnesium, if it loses one electron, then it will convert into magnesium plus. Atomic electron number will be 11. Now its electronic configuration 1s2, 2s2, 2p6. So one electron will leave from the 3s orbital. So it will become 3s1. Now again, if it loses another electron, it will convert into sodium plus 2, and electronic configuration will be 1s2, 2s2, 2p5. So electron will lose from this last orbital. Now in case of magnesium, it will convert into magnesium plus 2, at electron number will be 10, and electronic configuration 1s2, 2s2, 2p6. Now it loses electron from 3s orbital. Okay, so here look at the electronic configuration of this. Okay, so one electron elimination, one electron elimination, this is another electron elimination, this is another electron elimination. Okay, now look at the electronic configuration. This is not fully filled s orbital, so it is not stable. So less stable, you can say it is less stable electronic configuration. And here this is stable electronic configuration because s orbital is fully filled. Again here p orbital is fully filled, right? So it is stable electronic configuration, and this is not fully filled, so it is less stable, and here this is less stable, and here this is stable electronic configuration. Now if sodium loses one electron, in case of IE1, first ionization enthalpy, and in case of magnesium, the first ionization enthalpy of magnesium, using different color, just a minute, red, IE1, here IE1. Now look, in case of sodium, it is 3s1 and it is 2p6, so less stable to stable electronic configuration, and in this case it is a stable, and after losing one electron it becomes unstable. So stable stable electronic configuration to unstable electronic configuration. So you need to provide more amount of energy to lose electron from here to here. Okay, that means I1 of magnesium is greater than I1 of sodium. So I can say I1 of sodium is less than I1 of magnesium. Why? Because in case of magnesium, the electronic configuration is stable. So stable electronic configuration means it will not have a tendency to lose electrons. Uh, so if you want to remove electron from this stable electronic configuration, you need to supply more amount of energy. That means I1 will be more. But in case of sodium, look, it is not stable. So if it loses one electron, then it will become stable. So in this case, we don't need to supply more amount of energy to lose electron. That's why this I1 will be less than magnesium. Okay, now coming to I2. Now coming to I2. So look, this is the I2 of sodium and this is the I2 of magnesium. Now look, this is stable and this is not stable. So here from stable to unstable, it will not have a tendency to lose electron because here it is very much stable. So it will not have a tendency to lose electron. But if you want to lose electron, then you need to supply more amount of heat energy. More amount of heat energy you need to supply. But here this is not stable. This is not stable. And if it loses one electron, it will become stable. Okay. So in this case, just a minute. So in this case, IE2 of sodium is greater than IE2 of magnesium. Is it clear? I'm repeating it again. In case of IE2, sodium and magnesium. Look, sodium has a stable electronic configuration and sodium plus 2 has not, it is not stable electronic configuration. So from stable to unstable, it will not have a tendency. So if you want to lose electron, then you need to supply more amount of energy. That means IV2 of sodium will be more. But in case of magnesium plus 1, it is not stable. So if it loses one electron, it will become stable. So it has a tendency to lose electron because after losing electron, it will get a more stable electronic configuration. Okay, so in this case, we don't need to provide more amount of energy to lose electron from here. That's why I2 of magnesium will become less than I2 of sodium. So this is the kahani. Now I'm giving the statement. So here we have seen, just a minute. What we have seen, IE1 of sodium is less than IE1 of magnesium. Why? This is because the electronic configuration of magnesium is greater, is more stable, is more is more stable than more stable than sodium. Again, IE2 of sodium is greater than IE2 of magnesium. Why? This is because the electronic configuration of sodium plus is more stable than magnesium plus 1. Okay, so this is the answer of this question. Question may ask by this, using these two example. Another question, IE1 of lithium is less than IE1 of beryllium, but IE2 of lithium is greater than IE2 of beryllium. Why it is like that? Okay, if we go through with the electronic configuration, lithium, it has a 3 electron. Its electronic configuration 1s2, 2s1, and beryllium, it has a 4 electron. Its electronic configuration 1s2, 2s2. Okay, now if it loses 1 electron, it will convert into lithium plus, and its electronic configuration will be 1s2. Now again, in case of beryllium, if it loses 1 electron, so it will convert into beryllium plus, and electronic configuration 1s2, 2s1. Again, if it loses another electron, it will convert into lithium plus 2. Its electronic configuration will be 1s1. And if it loses 1 electron, then it will convert to E2 plus 1s2. Okay. Now look at the stability of the electronic configuration. This is not stable. One half filled, so not stable. Not stable. But you can say less stable. This is stable, and this is not stable, and this is stable. Here this is stable, this is less stable. Okay, now from not stable to stable, IE1, and this is IE2. Here in case of lithium, electronic configuration is not stable, and if it loses 1 electron, then electronic configuration becomes stable. So here we don't need to provide more amount of energy, because it has a tendency to lose electron, because after losing electron it will get the stability in its electronic configuration. So already it has a tendency to lose electrons, so we don't need to provide more amount of energy. Add for We don't need to provide more amount of energy to lithium atom to lose electron. But in case of beryllium, look, the electronic configuration is stable. Now if you want to lose electron, you need to provide more amount of energy, because it is stable here, so it will not have a tendency to convert into unstable electronic configuration, right? So if you want to lose electron, in this case you need to give more amount of energy, okay, to lose electron. That means IE1 of beryllium is greater than lithium, but IE2 of lithium will be greater than IE2 of beryllium, because look at the electronic configuration of lithium. It is stable and it is not stable. Okay, so from stable to unstable, it will not have a tendency to convert this to this. Okay, but if you want to lose, if we want to lose electron from lithium plus, then we need to provide more amount of energy. That means I will be greater. Okay. And in case of beryllium, look, this is not stable. So if it loses one electron, it will become stable. So here it has a tendency to lose electron, because after losing electron it will get a stable electronic configuration. That's why it has a tendency. So as it has tendencies, so in this case we don't need to provide more amount of energy. That's why IE2 of beryllium is less than IE2 of lithium. So this is the explanation actually here. Okay, just a minute, let me erase all the things. So here what we can say, IE1 of lithium is less than IE1 of beryllium, because electronic configuration of beryllium is more stable. Again, IE2 of lithium is greater than IE2 of beryllium, because here the electronic configuration of Li2 is more stable than the beryllium. Okay, so this is the answer over here. Now I'm moving to next topic. Hope this is clear to all. If you did not get anything, please, or if you have a doubt, please mention your doubt or query into the comment box. I will give you a reply, obviously. Okay, now coming to next topic. Hydrated ion. Radius of hydrated ion. Radius of hydrated ion, like lithium plus, say it is bonded with n number of water, sodium plus, it is surrounded by n number of water molecules, or next potassium, it is surrounded by n number of water molecules, and cesium, it is also surrounded by n number of water molecules. Okay, that means after dissolving in water, so they will convert into plus one charge, and this plus one charge will stabilized by water molecules. Because how they are stabilized, this is lithium plus, so positive charge is there, so water molecules has a lone pair oxygen. In water molecules, oxygen has a lone pair, so this oxygen lone pair will make a bond with, will make a bond, or you can say it will be surrounded by this water molecules. Now look at the radius over here. So this radius actually I am talking about here. Okay, so this is the radius from here to here. This is say R1. Okay, now again in case of sodium, it will be also surrounded by water molecules. Okay, it will be also surrounded by water molecules as like lithium. Similarly, potassium also and cesium also. Now the radius of this hydrated ion, which one will be which one will have a higher radius or higher diameter of the hydrated ion. Now, if I talk about lithium, if I talk about lithium, lithium is a smaller in size, right? Lithium ion, this ion, it is a smaller in size. Okay, smaller size means electron density, less, or we can say, so it is hungry for electron, hungry for electron, right? For which more number of water molecules, water molecules will come in its surface, in its surface, that is the radius, that is the radius will increase, because more number of water molecules come means the radius will automatically increase. Okay, now for the other hydrated ion, what happens, they have a larger size. Okay, they have a larger size. Larger size means they have lots of electron, lots of electron. Okay, lots of electron means they don't need electron from the lone pair of oxygen of water molecules. Okay, like cesium, if it loses electron again, still it has 54 electron. Okay, so it don't need electron from water molecules, say Cs plus, so it will make bond with water molecules. Now cesium, in case of cesium plus, it will not, it don't need electron from oxygen of water molecules, so less number of water molecules will come on the surface of cesium, because already cesium has a 54 electrons, so it is highly electron dense center. So because of high electron density on the cesium atom, it will not have a tendency to take lone pair of water molecules and make a bond. Okay, so the hydration tendency of this cesium ion will decrease. That means less number of water molecules will come on the surface of the cesium ion. That's why the radius will automatically decrease. So here the radius order. So we can say the radius order for this hydrated ions. For this hydrated ions, it will be like that. The most, this is the highest radius, and then this one, then this one, so this will be the least one. Okay, so just keep in mind that smaller size of cation, smaller size of cation means its hungriness for electron will be more because of having less number of electron. Okay, so more number of water molecules will come on its surface, that means its breadth of the surface will increase. Okay, and thereby the radius will also increase. So that is the thing. I'm writing this order here. For larger size cation, they have large number of electron, so they don't need don't need electron from that don't need electron from water molecules. Water molecules for which less number of water molecules will come on the surface, come on the surface of water, come on the surface of larger size metal ion, or thereby does the hydrated radius thus the hydrated radius will reduce, will be less. Okay, so this is the answer. Therefore, the order of hydrated radius of hydrated radius of alkali metal ion lithium plus aqueous, then sodium plus aqueous means water, then potassium plus aqueous, then cesium plus aqueous. Okay, this is the answer. Now coming to next question, next topic. You can now coming. Oh, sorry, what happened? Yes, okay. Now coming to next topic. Among these, among the alkali metal, potassium and cesium shows greater photovoltaic application. Photovoltaic application. Why? Photovoltaic application means solar cell. Solar cell application. What does it mean? It means potassium and cesium lose electron, can lose electron, and this electron can be stored in the solar cell device. Okay, that's why this. And now the question is that why only these elements, as like cesium and potassium, other alkali metals has also electron in their outermost shell. Actually, potassium and cesium has one electron in the outermost shell, so they can easily lose this electron. Okay, so to remove electron from cesium atom don't need to have a high frequency sunlight. Okay, so it can lose electron very easily because it has just one electron in its outermost shell. And also, okay, now the question is that why not the other alkali metals? Because as like these two elements, other alkali metals like sodium, lithium, they also have one electron in their outermost shell, but they are not possible to use. This is the reason. The reason is that because of the smaller size, their electron number is less, right? So they will not they will not lose electron. They will not lose electron with a normal frequency of sunlight. Okay, so sodium and potassium, because of the smaller size, they are strongly attracted by the nucleus. So in that case, normal sun ray, normal sun ray are not is not um, is not capable to remove electron from sodium and lithium. But in case of potassium and cesium, they have a large number of electron, and the last electron is present in the in case of cesium, the last electron is present in the sixth orbital. In the sixth shell it has one electron, and in case of potassium, uh, in fourth shell the last electron is present. So this last electron is not tightly bonded with the nucleus. Okay, now if sunlight falls on this potassium or cesium metal, they can easily lose the electron. Again, another thing is that sodium, you can't sodium and lithium normally because they are very reactive towards water, towards oxygen, towards water, so they will convert into compound. Okay, that's why sodium and lithium, that are not possible to keep them in free state in nature. Okay, so if you keep them, they will react with water molecules vigorously. That's why it is very difficult to handle sodium also. And we know sodium, we need to keep it in under kerosene or petroleum ether. Okay, so sodium, whenever sodium comes in contact with water, it will react vigorously. Okay, for which we need to keep them in under kerosene. That is also can be one reason that sodium, we can't keep them in free states. Again, other than this, potassium and cesium, the last electrons is in the fourth shell, for which these two electrons are not tightly bonded by the nucleus. So normal sun ray can remove the electron from potassium and cesium. That's why these two elements are can be used in photo solar cell application. Okay, so if I give a statement for this answer, I will just write because of larger size, the outermost 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 one electron is not tightly bonded with the nucleus, for which it becomes easier to remove electron from their outermost shell. That's why they can be used in the photovoltaic photovoltaic application. In the photovoltaic applications. Okay, now coming to another topic. Coming to another topic, alkali metals. Alkali metals and their salt or their salt exhibit a characteristics color in flame test. And why? Okay, the question is that alkali metals exhibit various characteristics color in flame test. Why? And what are the different colors? Let's see. In case of lithium, lithium exhibit crimson red color. Crimson red color at lambda 670 nanometer. At around sodium exhibit golden yellow. Golden yellow color at lambda 590 around nanometer. And potassium exhibit violet color. Violet at lambda, you can say 766 nanometer. And rubidium exhibit red violet at lambda 780 nanometer. And in case of cesium, the color becomes blue and the lambda 4 4 455, sorry, 455 455.5 nanometer. So they exhibit different color at a different wavelength. Okay, now the thing is that why they exhibit such kind of colors. Okay, why they exhibit such kind of colors in flame test. Okay, now we can explain this in this way. Alkali metal has one electron in their outermost shell. In their outermost shell. So while providing energy to them, or when we take or bring them towards into flame. The last electron, last shell electron absorb this energy, and excited into the excited into the higher energy level. Into the higher energy level. After sometimes when heat energy is removed, the electron come back to its original state. To its original state by emitting energy as a colored ray. As a colored ray. That's by this way they exhibit color. They exhibit characteristics color. In flame test. Okay. So this is the kahani. Actually, what happens, say in case of lithium, so 2,1, so it has one electron in the second shell, right? So if you provide energy, so it will go in the third shell, it will go in the fourth cell. Okay, now when you remove the energy, again the electron from fourth to third or second, that means it will come into the second to its original position. Okay, so while coming back from higher energy level to lower energy level to its original state, it will lose the that amount of energy whatever it has taken to go into the state. Okay, so that exactly equal amount it will lose. Okay, it will lose, and it will lose here as a colored ray. Okay, and because of which we are getting different color, we are getting characteristics color. Now if you say why they exhibit different color, why the color is not same, because the element is different, their size is different. Because of different size, the electronic the electron and the nucleus attracted the nucleus attracted the electron more strongly if element is a lower size. So for example, in case of lithium, its size is less, so the outermost electron is very close to the nucleus. So for lithium atom, if you want to excite this electron, you need to supply more amount of energy. More amount of energy means it is absorbing high frequency light ray. Okay, so when it is coming back to its original state, so of exactly equal amount of energy it will lose. So for each of the atoms we need to supply different amount of energy because their radius is different. So to excite to each of the elements we need to supply different energy because of the different radius of the elements. Okay, so this is the main thing. Okay, so up to this much for today's class. I will upload it, and the remaining materials of this chapter, you will get it in the next videos. Okay, so don't forget to subscribe, and thank you for watching. Tata, bye bye, take care.